Hello friends, welcome back to You Can Do TV. A reactor pressure vessel weighing 330 tons. 4 steam generators at 365 tons apiece. Fuel assemblies flown into Akkuyu from Novosibirsk under radiation monitoring at every checkpoint. And a plant engineer to ride out a magnitude 7 earthquake without shutting down. How does a stretch of Mediterranean coastline become a working nuclear plant? Stick around near the end, the exact moment Akkuyu stops being a construction site. Try counting the trucks on this coastline, and you'll give up around number 400. Over 2,500 vehicles and heavy machines run across this footprint every single day. Excavators, dump trucks, tower cranes, crawler cranes, and rows of concrete mixers all moving at once, feeding one of the biggest nuclear builds anywhere on Earth right now. Strip away the cranes and the trucks, and here's what all this dirt at Akkuyu is really being moved for. Molten steel poured in Volgodonsk, glowing forgings hammered into reactor pressure vessel rings, fuel assemblies built in clean rooms in Novosibirsk, circulation pumps machined in Podolsk, control cabinets wired in Yekaterinburg. Each piece travels thousands of kilometers only to end up as part of one working nuclear power plant. Try shipping one component wrong and Akkuyu's schedule slips by 6 months. The real question is how this stretch of coastline turns into a facility capable of running a nuclear reactor. This is how a coastline becomes a power plant. Turn it into the largest nuclear construction site on the planet first. 1,300 vehicles working the site daily, 11,000 people on the ground, a dedicated maritime cargo terminal purpose-built to receive components that would shatter a normal port crane on lift day. And here's where the numbers stop feeling like a press release. 4 VVER 1,200 reactors going up in parallel, 1,200 megawatts each, designed for 60 years of service with a possible 20-year extension. Once all 4 units are running, output hits 35 billion kilowatt hours a year. Wow! Enough to cover about 10% of Turkey's electricity needs. Most people picture Turkey's grid as coal and gas heavy, with a slow, renewable ramp. That 10% from Akkuyu says otherwise. Where do you actually see nuclear fitting into the country's mix by 2035? Then there's the unglamorous part almost nobody thinks about. Try pouring a reactor foundation without a concrete plant sitting right next door. The on-site batch plant runs 30 different concrete classes and pushes out 3,000 cubic meters a day. Reactor zones get heat-resistant special mixes. And behind the concrete comes the steel, a lot of steel. Roughly 100,000 tons of iron and steel products flow into the site every year. Plate cutting on automated lines, rebar bending by machine, ultrasonic testing on welded pipe sections. When people say megaproject, this quiet logistical backbone is what actually earns the word. You don't see it in the drone shots. And a workforce this size has to renew itself. Interns arriving on site, the next crew that will run these reactors after today's builders go home. A plant designed for 60 years needs people trained to think in decades. Every nuclear build hits one construction moment that has to be right the first time, because after this, getting back inside gets exponentially harder. The inner containment structure goes up around the reactor zone in stacked cylindrical tiers. A recent tier on Unit 1 weighed 322 tons and took roughly 24 hours to hoist and land into position. 24 straight hours to lower one steel ring. Get out of here. Every weld line, every anchor point, every fit tolerance has to line up before the next tier can go on top. And how do you actually lift something that heavy without breaking it on the way up? A traverser, a custom lifting frame with multiple articulated arms, engineered specifically for this project, spreads the load so a 300-plus ton dome section rides in balance. Then the reactor building gets its own permanent muscle. The main bridge crane commissioned inside is what will move every heavy component in and out, including the reactor pressure vessel itself. Once this crane runs, the space becomes capable of handling the equipment that defines a nuclear plant. And that equipment is about to arrive. And here comes the one component the plant hopes to never need. The core catcher, 169 tons, 5.8 meters tall, 6.1 meters across, is a passive safety device designed for a severe accident scenario where the reactor core actually melts through. If that ever happens, molten fuel drops into the catcher instead of the containment floor. The design distributes the heat, prevents ground contact, and keeps radiological release inside the plant. Rated for extreme seismic loads, hydrodynamic pressure, and impact resistance. Almost nobody sees this piece of hardware. Almost nobody wants to. A nuclear plant is judged not by what it does on a normal day, but by what happens on the worst one. The reactor pressure vessel is where nuclear fission actually happens, the heart of the entire plant. 330 tons, 4.5 meters across, 12 meters tall, manufactured over roughly 3 years, cleared through 300-plus quality control tests, and shipped nearly 3,000 kilometers by land and sea to reach the site. One vessel isn't enough on its own. The reactor's heat has to become steam before it becomes electricity. Steam generators bridge that gap. 4 of them per unit, each around 365 tons, each a horizontal cylindrical vessel with elliptical heads. Inside sits a bundle of tubes carrying primary loop coolant at high pressure, while feed water flashes to steam around the outside. Picture yourself as the plant operator on hot commissioning day. One of 4 steam generators shows a marginal pressure test result. Do you delay startup weeks to swap it, or accept the reading and monitor? Comment below. A reactor doesn't actually produce electricity, it produces heat. Turning that heat into a moving current takes a machine on a whole different scale. The largest last-stage blade ever built for a nuclear turbine measures 75 inches. Sitting inside an 8-meter-wide bladed module, spinning at 1,500 revolutions per minute, that blade is what defines the upper limit of what a single turbine can deliver, around 3.2 gigawatts of clean output once the assembly is finished. And a turbine on its own doesn't finish the job. A nuclear turbine island is a full ecosystem. Steam lines, condensers, feed water loops, generator, and the crane infrastructure that puts it all together inside one hall. Modules pre-assembled in factories get shipped overland in yellow escorted convoys that shut down rural roads for entire nights. On-site, giant red gantry cranes maneuver each piece into position with margins measured in millimeters. You can build the fanciest reactor in the world, but if the turbine hull can't move the yellow blob into place cleanly, the project stalls. And here's what that looks like on the Akkuyu floor. The turbo generator stator, the heaviest single piece of equipment in the plant, roughly 430 tons, 12 meters long, 4.2 meters across, lifted crane-free by a hydraulic rigging system onto 18-meter columns and rolled into position on a dedicated rail. Every rotating device on this scale gets tested before it ever touches the plant. A modern feedwater pump, 13 megawatts, 90 bar discharge, 15 meters long, 110 tons, has to prove it can run at full load without vibration pulses that would crack downstream piping. Look closely at one component almost nobody outside the industry has ever heard of. And here's where a nuclear plant either stays running or gets shut down cold. The reactor coolant pump keeps primary loop water circulating between reactor and steam generator. At the point where its rotating shaft passes through the pump housing, there's a mechanical seal, and if that seal fails, the pump stops, and the plant stops with it. The engineering fix is a three-stage design. Each stage carries a share of the total system pressure, and if two stages fail simultaneously, the remaining stage is engineered to hold full pressure by itself. The sealing faces get an advanced silicon carbide material for wear resistance, and every unit runs through a full simulator matching real operating conditions before it ships. A three-stage backup on one seal, that's how paranoid nuclear engineering gets when the stakes are this high. And the plant doesn't need these components once. It needs them cared for over 60 years. Reactor coolant pump refurbishment, motor rewinding, seal changeouts, radiological machining. Whole service centers exist purely to keep rotating equipment inside nuclear plants running, which is exactly what the plant is built to defend against on the worst day. The reactor building sits inside two nested containment shells, together about 2 meters thick, engineered to survive earthquakes, tsunamis, and a 7-ton aircraft strike at 100 meters per second. A jetliner hitting the dome at that speed and it just holds? No way. And the whole safety idea rests on one principle. Never trust a lone line of defense. Physical layers, active systems, passive systems, and control redundancy all integrated in parallel with civil construction. Honestly, passive safety is the most underrated engineering leap of the last 30 years in this industry. Let us know what you think. Which raises the harder question: when does construction actually end and operation begin? Now watch this animation with everything you've just seen at Akkuyu in Hinkley loaded into your head. The reactor sits at the center, 14.6 meters tall, 4.5 meters across, carbon steel alloy, nuclear fuel below, control rods above, fuel assemblies made from uranium pellets sealed inside ceramic, stacked into rods, bundled together in the hundreds. Coolant flows through the fuel at roughly 150 times atmospheric pressure. 4 reactor coolant pumps push enough water through the primary loop to fill an Olympic pool in about 1 minute. The heated coolant travels through 13,000 U-shaped tubes inside each steam generator, boiling feed water on the outside. Steam rotates the high-pressure turbine first, gets reheated through a moisture separator, then drives 3 low-pressure turbines. Seawater in the condenser cools the exhaust back to liquid, creating a near vacuum that pulls even more force from the turbine cycle. Around all of it sits containment, a dome 45 meters across, 75 meters tall, walls 1.2 meters of reinforced concrete, 5 radiation barriers, fuel pellet, fuel rod cladding, reactor vessel, steel plate lining, and the outer concrete wall itself. The plant is engineered to automatically shut down at a magnitude 6.5 earthquake and keep functioning safely up to magnitude 7. Emergency diesel generators sit above ground behind waterproof barriers. Main control room runs on distributed control across dual reactor units. Foundation built on excavated bedrock rather than soil. Everything's shipped, welded, poured, tested, and rigged across 2 continents ends up as one integrated machine that runs quietly for 60 years. The biggest thing about a nuclear plant isn't the reactor vessel or the crane. It's the coordination required to make thousands of parts behave as one machine. Here's where the whole question flips from how much is built to does any of this actually work? Inside Unit 1, 163 dummy fuel assemblies, identical in size, weight, and design to real nuclear fuel, get loaded into the reactor pressure vessel to rehearse mechanical fit and hydraulic behavior. Site progress footage tells you something written reports can't. Reactor buildings closing up, dome sections landing on top, cranes swinging over 4 units at once. Roughly 200 buildings and structures on this single site by full completion. And the closer commissioning gets, the more the work shifts underground. Cabling, piping, instrumentation, integration testing across systems that all have to talk to each other before a fuel rod ever enters the core. The foundation for Unit 4 gets poured, while Unit 1 already runs pre-commissioning tests. 4 reactors moving at once, at different stages, on the same schedule. Total plant output when everything is running, 4,800 megawatts. Welders on scaffolding at sunset, surveyors framing rebar cages, concrete pours running through the night. The tunnel isn't the darkness. The light coming out the other end is the country's grid getting a new baseline load. And this is the moment the project stops being a construction site. The first batch of nuclear fuel arrives at Akkuyu, manufactured in Novosibirsk, moved by truck to airport, flown to Adana, and escorted onto the site under radiation monitoring at every checkpoint. The instant those fuel assemblies enter the fresh fuel storage, Turkey officially joins the club of countries operating nuclear generation on their own soil. Full commissioning will cover about 10% of national electricity demand and cut roughly 18 million tons of CO2 emissions a year. None of this works without millimeter-perfect surveying from day one. Every foundation and equipment anchor traces back to a control network established before excavation began. Which raises another question. Is Akkuyu the exception or the new standard? Akkuyu isn't the only site solving this puzzle right now. At Hinkley Point C, another 2-unit nuclear plant has been rising on the coast of southwest England since 2016. Time-lapse footage across 5 years shows what a nuclear megaproject actually feels like from the air. Bare earth in 2016, seawalls and coastal defense in 2018, Reactor foundation with round formwork in 2019, blue steel framework in 2020, heavy lift barges maneuvering by 2021. Then comes the poor engineer's actually name, J0, 9,000 cubic meters of concrete in one continuous placement, reinforced with 5,000 tons of Welsh steel, laid over 6 months by a joint venture crew. Officially the largest concrete pour in UK history, and it holds the entire reactor above it. And this is where modular nuclear construction stops being a slide in a presentation. Rebar cages weighing 170 tons, 14 prefabricated units for a staircase structure, get pre-assembled in a satellite yard, then lifted onto Unit 2's reactor building in one hoist by a bespoke lifting beam and the world's largest land-based crane. Same site, second reactor pressure vessel, lifted into place by the biggest crane on the planet. Building two identical units side by side isn't a stunt. It's how the second unit gets built faster and cheaper than the first, because every lesson from Unit 1 lands directly into Unit 2's schedule. Unit 1 is 40% over budget. Unit 2 is running 20% faster than Unit 1's pace. Do you keep pushing through both, or freeze Unit 2 until Unit 1 finishes clean? The precision installation happens with millimeter tolerance inside a fully enclosed containment building, guided by rigging engineers standing meters from a component that weighs several hundred tons. And on the turbine island side, something else lands in the hall. The world's largest electricity generator stator, 450 plus tons, 12 meters long, arrives on a wheeled trailer and rolls straight into Unit 1's turbine hall. Inside, a massive gantry crane hoists it clear. Workers strip protective wrapping, and specialist crews position it on temporary stools ready for coupling later. Once mated to the turbine, this single machine will feed low-carbon electricity to roughly 3 million homes. And here's the part of a nuclear plant almost nobody thinks about. Cooling water doesn't just show up. Concrete intake heads get precast onshore, transported on multi-wheeled trailers, loaded onto barges via ballast pumping, and towed offshore under tug escort. Then, two of the biggest floating cranes on Earth lift these 5,000-ton concrete structures off the barge and lower them onto the seabed. Bristol Channel, second highest tidal range on the planet, 5,000 tons placed on the ocean floor to the meter. That's insane. All 4 steam generators installed, pressurizer welded into the primary circuit, 220,000 supports being fitted, 700 kilometers of pipe, 10,500 kilometers of cable, enough to wrap a quarter of the way around the planet. Peak construction, every discipline running at once. Every scene in this video circles back to one uncomfortable truth about nuclear construction. The technology has been proven for decades. What remains difficult is the political, financial, and organizational coordination around it. Akkuyu is being built under a build, own, operate model with Rosatom financing. Hinkley Point C has faced major cost overruns and delays, putting pressure on UK energy policy. Small modular reactors promise shorter construction schedules, but commercial deployment at scale is still ahead. So here's the honest split. Do you believe the future of clean baseload energy runs on giant gigawatt reactors like Akkuyu and Hinkley, or on fleets of small modular units built in factories? Tell me where your bet actually sits below. If pulling the curtain back on how modern industry gets made keeps you watching, hit subscribe. The next build going up is even wilder. See you. Take care.